11 seconds. That is all the time you would have. Not minutes, not hours. 11 seconds from the moment you step onto the rust-colored surface of Mars without protection until consciousness begins to fade. 11 seconds before your body, evolved over millions of years to thrive in Earth's embrace, begins its catastrophic surrender to a world that was never meant to hold human life. In those 11 seconds, everything you think you know about dying in space would prove incomplete. The movies show explosive decompression, bodies freezing instantly, blood boiling in the void. But Mars is not the void. Mars is far stranger, far more patient in its cruelty. What kills you there is not what most imagine. It is not the cold, though temperatures plunge to 80 degrees Celsius at night. It is not the thin atmosphere alone, though it holds less than 1% of Earth's pressure. It is something more immediate, more primal, hidden in the very air, or rather the absence of it, that would begin dismantling the delicate machinery of human survival before you could even form a final thought. Tonight, we journey to the fourth planet, not as explorers arriving in triumph, but as biological experiments testing the limits of human fragility. We will trace the timeline of survival across multiple scenarios, from the instant death of exposure to the theoretical years of permanent habitation. We will discover that Mars kills in layers, each scenario revealing new threats that wait patiently beneath the surface, invisible yet relentless. How long could you truly survive on Mars? The answer depends not just on technology, but on understanding the precise mechanisms of death that this world offers. Some would claim mere seconds. Others might point to future colonies lasting decades. Both are correct. Both are incomplete. The truth exists in gradients, in scenarios that stretch from heartbeats to harvests, from suffocation to starvation, from radiation poisoning to psychological collapse. Across the 140 million miles of space that separate us from Mars at its closest approach, we have sent rovers and landers to study its surface. They have returned images of breathtaking desolation, ancient riverbeds carved by water that vanished billions of years ago, towering volcanoes that dwarf anything on Earth, dust storms that engulf entire hemispheres for months. Yet these mechanical ambassadors cannot tell us what it feels like to stand there, to breathe, or fail to breathe, to watch time become your enemy as resources dwindle and your body slowly recognizes. It is fighting a losing war against an environment that offers no compromise. If you enjoy these explorations of human limits and cosmic realities, please like this video and subscribe to journey further into the extraordinary and terrifying truths about our solar system. And before we step onto that alien surface together, tell us in the comments, where are you watching from right now? What time is it in your corner of Earth? It reminds us that no matter how far we travel in imagination, we are all still here, still connected by the atmosphere and gravity that make these 11 seconds feel impossibly short. Now, let us begin the countdown. Let us examine what Mars truly offers to the unprotected human form. The scenario is simple, almost absurdly so. You step out of a spacecraft onto the iron oxide dust. You are wearing nothing. No spacesuit, no helmet, no gloves. Just skin and bone and the fragile biology that keeps you conscious. The sky above is a pale butterscotch colour, tinted by perpetual dust. The sun appears 2/3 the size it does from Earth, distant and cold. The landscape stretches endlessly in muted reds and browns, beautiful in its starkness, utterly indifferent to your presence. And then the countdown begins. Not toward launch, but toward darkness. 11 seconds until your world narrows to a pinpoint and extinguishes. This is not speculation. This is physiology meeting physics. This is what happens when Earth's children step beyond the garden that made them. But 11 seconds is only the beginning of the story. The question is not just how quickly Mars can kill you. The question is how long, under different circumstances, you could learn to survive. And the answers may surprise you. Imagine standing at the airlock of your Mars habitat. Through the reinforced glass, the rusty landscape stretches endlessly beneath a butterscotch sky. For a moment, curiosity overwhelms caution. What would happen if you simply stepped outside without protection? No spacesuit, no helmet. Just you and the raw Martian atmosphere. The answer is not instantaneous obliteration, as Hollywood might suggest. It is something far more disturbing. A precisely choreographed cascade of biological failures that would unfold over exactly 11 seconds. 11 seconds between exposure and unconsciousness. 11 seconds to experience what no human body was ever designed to endure. The moment the airlock opens, the first thing you would notice is not pain, but sensation. Mars's atmospheric pressure is less than 1% of Earth's, roughly equivalent to standing 100,000 feet above our planet's surface, 3 times higher than commercial aircraft fly. Your body, pressurized from within by fluids and gases calibrated for Earth's atmosphere, suddenly faces a near vacuum. But here is where popular science gets it wrong. You would not explode. The human body is not a balloon. Our skin is remarkably strong, a flexible membrane capable of containing internal pressure, even when external pressure drops dramatically. Astronauts who have experienced accidental depressurization in training chambers have survived with only minor injuries. Your body would swell, yes, perhaps increasing in size by 10 to 15% as dissolved gases expand in your bloodstream, but your skin would hold. The terror lies not in rupture, but in what happens beneath the surface. Within the first second, something called ebulism begins. At Mars's low atmospheric pressure, the boiling point of water drops to the temperature of the human body. The moisture on your tongue begins to bubble. Saliva boils not from heat, but from pressure, forming foam that fills your mouth with a strange, fizzing sensation. Your eyes, covered in a thin layer of tears, experience the same phenomenon. The fluid on your corneas starts to vaporize, creating a mist that clouds your vision almost immediately. It is a surreal experience, watching the world blur, not from injury, but from your own body's moisture turning to vapor in the alien air. Some researchers suggest you might feel a tingling sensation across your skin as moisture evaporates from pores, drawing heat away so rapidly that exposed areas begin to freeze, even as others feel strangely warm from internal swelling. By second 3, your lungs face an impossible choice. The air you're trying to breathe is 95% carbon dioxide, toxic and useless for respiration, at a pressure so low it cannot sustain gas exchange in your alveoli. If you instinctively hold your breath, the pressure differential would cause severe barotrauma, potentially rupturing lung tissue as gases expand. If you exhale and try to breathe the Martian atmosphere, you simply circulate poison. There is no winning scenario. Your body begins making choices without your consent. Oxygen stored in your bloodstream is being consumed by cells desperate for fuel, but no new oxygen arrives to replace it. Your brain, which uses 20% of your body's oxygen, despite being only 2% of your mass, begins its countdown to shutdown. The cold becomes apparent by second 4 or 5, though perhaps not in the way you'd expect. Mars's average temperature hovers around -80 degrees Fahrenheit, but temperature in a near vacuum behaves differently than on Earth. Without air molecules to conduct heat away from your body, you don't freeze instantly. Instead, you lose heat through radiation and evaporation. The moisture boiling off your skin actually draws heat away faster than the cold air itself. Your extremities, your fingers, your nose, your ears would begin to ache with a deep, penetrating cold, while your core remains temporarily warm, creating a disorienting sensation of being simultaneously frozen and feverish. Some scientists theorize that the areas where moisture evaporates most rapidly, inside your mouth, your nasal passages, and around your eyes, might actually experience localized frostbite within these first few seconds. Radiation, the invisible destroyer, begins its work immediately, though its effects in this brief window are almost negligible compared to other factors. Mars lacks Earth's protective magnetic field and thick atmosphere. Cosmic rays and solar radiation strike the surface directly, delivering a dose roughly equivalent to receiving 20 chest X-rays every hour. In 11 seconds, you'd absorb perhaps 6 or 7 hundredths of a chest X-ray worth of radiation. Enough to damage some cells, certainly, but nowhere near enough to matter in the context of what's happening to the rest of your body. The radiation is playing the long game. It's the other elements of Mars that kill quickly. By second 7, your brain begins to fail. Hypoxia, the lack of oxygen, has progressed beyond the point of recovery. Interestingly, you might experience a phenomenon reported by high-altitude climbers and pilots who've lost cabin pressure, a strange sense of euphoria. As oxygen levels plummet, the brain doesn't always register danger. Instead, some people feel an odd tranquility, a disconnection from reality that might almost be merciful given the circumstances. Your vision, already clouded by evaporating tears, begins to tunnel. Colors fade. The rust-red landscape of Mars might appear grey, or washed out as your visual cortex struggles with insufficient oxygen. You might see spots or flashes of light, neurons firing randomly as systems fail. Second 8 or 9 brings confusion. If you're still conscious, your thoughts become fragmented, dreamlike. You might forget where you are or why you're cold. This cognitive decline happens faster than most people imagine. Fighter pilots trained in high-altitude chambers lose useful consciousness in as little as 6 to 8 seconds when exposed to similar pressure drops. You are not thinking clearly enough to feel panic. Your body's autonomic systems continue working, your heart racing, trying desperately to pump oxygenated blood to vital organs, but it's pumping blood that contains progressively less oxygen with each beat. Your muscles, starved of fuel, begin to weaken. If you tried to move, you'd find your limbs heavy, unresponsive. By second 10, unconsciousness is imminent, or has already occurred. Your brain, magnificent and complex, designed for Earth's oxygen-rich environment, simply cannot function in this alien atmosphere. You would collapse, probably without feeling the impact of hitting Mars's iron oxide dust. In experiments with rapid decompression, subjects report that the transition to unconsciousness is not gradual. There's no slow fade to black. One moment you exist, aware and present, and the next, nothing. The boundary is sharp, decisive. Second 11 marks the end of awareness, though not necessarily the end of life. Your heart might continue beating for another minute or more, stubbornly pumping blood through a body that can no longer use it. Cellular death takes time. Your brain cells would survive for perhaps 3 to 4 minutes without oxygen before irreversible damage occurs. If, hypothetically, someone pulled you back into a pressurized environment within that narrow window, aggressive medical intervention might perhaps restore some function. But the damage from embolism, from the expansion of gases in your tissues, from the profound disruption of every system in your body would be catastrophic. This is the terrifying truth about Mars's lethality. It doesn't destroy you with dramatic violence. It doesn't tear you apart or incinerate you. Instead, it simply removes the conditions necessary for human life to exist, and your body, exquisitely adapted for Earth, unravels with quiet, methodical efficiency. 11 seconds is simultaneously an eternity and an instant, long enough to experience the wrongness of an alien world, but not long enough to truly comprehend what's happening. The human body, remarkable in its resilience, has no defense against an environment this fundamentally hostile. In those 11 seconds, Mars doesn't kill you through any single mechanism. It kills you through all of them at once, a symphony of biological failure that reminds us just how precious and fragile our Earth-born existence truly is. The spacesuit is humanity's most intimate spacecraft, a personal vessel engineered to sustain life in the absolute hostility of space. On Mars, wrapped in this technological cocoon, you are no longer naked to the void. You have bought yourself time. Not days, not weeks, but precious hours that stretch between survival and oblivion. Yet even this marvel of engineering, this culmination of decades of research and billions in development, cannot hold back death indefinitely. It can only postpone it, transform it from an instant annihilation into a slow countdown measured in oxygen molecules and battery power. Modern spacesuits designed for Mars are far more advanced than those worn on the Moon in the 1960s. They are pressurized shells maintaining approximately 4.3 pounds per square inch of atmosphere, enough to keep your blood from boiling and your lungs from collapsing. The suit's outer layers are woven from materials designed to withstand temperatures that swing from 70 degrees Fahrenheit in direct sunlight to minus 100 degrees in shadow. Inside, a network of tubes circulates temperature-controlled water across your body, preventing you from freezing or overheating as you move. Every component serves a purpose. Every system has a backup, and yet every system has limits. The most critical element is oxygen. A standard Mars spacesuit carries approximately 6 to 8 hours of breathable air stored in high-pressure tanks mounted on the backpack. This is not an arbitrary number. It is calculated based on metabolic rates, exertion levels, and the physical capacity to carry compressed gas without making the suit impossibly heavy. As you breathe, your body consumes oxygen and produces carbon dioxide. In a closed system like a spacesuit, that CO2 must be scrubbed from the air, or it will accumulate to lethal concentrations within minutes. Lithium hydroxide canisters absorb the carbon dioxide, transforming it into a harmless solid. But these canisters have finite capacity. When they saturate, CO2 begins to build in your helmet. First comes dizziness, then confusion. Your breathing becomes rapid and shallow. Eventually, you slip into unconsciousness, not from lack of oxygen, but from poisoning by your own exhalations. 6 to 8 hours. That is your window. In ideal conditions, moving slowly, conserving energy, staying calm, you might extend this to the upper limit. But Mars is not ideal. Every step through the regolith demands energy. Every movement against the suit's pressurized joints requires effort. Your heart rate increases. Your breathing deepens. Oxygen consumption accelerates. What was 8 hours becomes 6, then 5. The clock does not pause. It counts down with every breath. Battery power adds another constraint. Your suit's life support systems, heaters, communication equipment, and the motors that assist joint movement all draw from a single battery pack. Current prototypes can sustain full functionality for approximately 6 to 10 hours, depending on environmental conditions and activity level. As temperatures on Mars plummet during the evening or in shadowed regions, the heating system draws more power. If you find yourself in direct sunlight for extended periods, the cooling system activates, consuming energy to prevent overheating. There is no neutral state on Mars. Every environmental extreme demands a response, and every response drains your reserves. The moment your battery depletes, systems begin to fail in sequence. First, auxiliary functions shut down, communications, environmental monitoring. Then the heating coils stop circulating warm fluid. Within 20 minutes, the cold begins to penetrate. Your fingers and toes grow numb. Your core temperature drops. Hypothermia does not wait for permission. In Mars's thin atmosphere, there is no air to trap warmth around your body. Heat radiates away into the void with ruthless efficiency. Even a fully pressurized suit cannot protect you from freezing when its thermal systems fail. Then, there is the question of suit integrity. A puncture in a spacesuit on Mars is not the explosive decompression depicted in films. The Martian atmosphere exerts almost no external pressure, meaning a small hole would cause a slow, steady leak rather than a catastrophic blowout. A tear the size of a pinhole might take 30 minutes to drain your suit to dangerous pressure levels. Larger punctures accelerate the timeline. A rip in the fabric from falling on sharp volcanic rock could empty your suit in minutes. NASA has developed emergency patch kits, self-sealing fabrics, and pressure-maintaining protocols. But these are temporary measures. A compromised suit is a ticking clock within a ticking clock. Real-world Mars mission simulations have illuminated the physical toll of extended spacesuit use. During NASA's Hera and High Seas analog missions, participants wore pressurized suits for hours while conducting surface operations. They reported profound physical exhaustion. The suit's resistance to movement transforms even simple tasks into labor-intensive efforts. Bending to pick up a rock sample, climbing a slope, kneeling to examine soil. Each motion fights against the pressurized joints, fatiguing muscles far faster than the same activity would on Earth. After 3 hours, participants noted significant decreases in dexterity and cognitive function. After 5 hours, some could barely manipulate tools. The suit, designed to preserve life, simultaneously constrains it. Interestingly, some researchers have proposed hybrid approaches for Martian exploration. Partial pressure suits that maintain lower internal pressures, reducing joint stiffness and improving mobility. These designs could extend operational time by reducing physical fatigue and lowering oxygen consumption rates. Yet they introduce new risks. At lower pressures, decompression sickness becomes a concern if a suit fails. The balance between mobility and safety is a razor's edge, and every choice carries consequences. There is also the question of cognitive endurance. Isolation inside a helmet, limited peripheral vision, the constant hum of fans and pumps. these factors accumulate into psychological strain. Studies from Antarctic research stations and long-duration space missions reveal that sensory deprivation and monotony erode decision-making abilities. On Mars, wearing a suit for 8 hours, you are alone inside your helmet. The landscape outside is red and unchanging. Communication with a habitat may be intermittent. Time dilates strangely when your world is reduced to the small window of a visor and the rhythm of your own breathing. Mistakes happen not from lack of training, but from the slow erosion of focus that comes with prolonged isolation in a hostile environment. Some engineers theorize that future suits could incorporate regenerative life support systems, recycling exhaled CO2 back into breathable oxygen through chemical processes. If such systems prove viable, operational time could extend to 12 or even 24 hours. But these technologies remain experimental. Current prototypes are heavy, power-intensive, and prone to failure in dust-laden environments. Mars's pervasive regolith clogs filters, jams mechanical components, and abrades seals. What works in a laboratory on Earth may falter on Mars, where conditions are unforgiving and repair options are limited. The reality is this: a spacesuit on Mars buys you hours, not days. It transforms instantaneous death into a slow countdown, giving you time to return to safety, to reach a habitat, to signal for rescue. But it is not a solution. It is a temporary shield against an environment that does not tolerate human life. Every minute outside extends the risk. Every hour depletes reserves that cannot be replenished without returning to shelter. In this, the spacesuit is both miracle and prison. It allows us to walk on an alien world, to touch Martian rock, to stand beneath a sky coloured by iron dust. Yet it reminds us constantly of our fragility. We are not built for this place. We are visitors in pressure vessels, carrying fragments of Earth's atmosphere in tanks on our backs, holding on to warmth borrowed from batteries, breathing recycled air that grows staler with each passing hour. The spacesuit does not conquer Mars. It negotiates with it, buying time in exchange for careful planning, constant vigilance, and the knowledge that every second beyond its operational limits brings you closer to the edge. Survival in a spacesuit is not about endurance. It is about respecting the boundaries of technology and the relentless mathematics of life support in a place where life was never meant to exist. Even with a spacesuit protecting you from the vacuum and cold, even with a habitat shielding you from the dust storms and thin atmosphere, there is another threat on Mars, one that cannot be seen, heard, or felt, one that does not announce its presence with alarms or sudden pain. This threat arrives silently, penetrating walls, passing through fabric, moving through flesh and bone with the indifference of cosmic law. It is radiation, and on Mars, it is everywhere. To understand the danger, we must first understand what Earth provides that Mars does not. Our planet is wrapped in an invisible shield, a magnetic field generated by the churning molten iron in Earth's core. This magnetosphere extends thousands of miles into space, deflecting charged particles from the Sun and cosmic rays from distant galaxies. It is a planetary force field that we never notice, yet without it, Earth's surface would be scoured by radiation levels lethal to most life as we know it. Mars once had such a field. Billions of years ago, its core was hot and active, generating magnetic protection much like Earth's. But Mars is smaller, and its interior cooled faster. The dynamo that powered its magnetic field shut down, perhaps 3.5 billion years ago. When that happened, Mars was left exposed to the cosmos, stripped bare of its primary defense. The solar wind gradually eroded much of its atmosphere, thinning it to less than 1% of Earth's density. What remains offers almost no shielding from radiation. Standing on Mars is, in many ways, like standing on the surface of a world that has been cosmically abandoned. The numbers tell a stark story. On Earth, the average person receives about 2 to 3 millisieverts of radiation per year from natural background sources, cosmic rays filtered through our atmosphere, radon gas seeping from rocks, trace elements in food and water. Astronauts aboard the International Space Station, orbiting above most of Earth's atmosphere, but still within the magnetosphere's protection, receive about 144 millisieverts per year. On the surface of Mars, a human being would absorb approximately 250 millisieverts annually, more than 80 times the radiation dose of someone living on Earth. But this figure assumes calm conditions. It does not account for solar storms. The sun is not a steady, unchanging light. It roils with magnetic activity, erupting periodically in solar flares and coronal mass ejections that hurl billions of tons of charged particles into space. When these solar particle events strike Earth, our magnetosphere deflects most of the radiation, and our thick atmosphere absorbs the rest. We may see auroras dancing in the polar skies, beautiful curtains of green and violet light. But on Mars, there are no such protections. A solar particle event that would produce stunning lights on Earth could deliver a radiation dose on Mars equivalent to receiving hundreds of chest X-rays in a matter of hours. NASA's Curiosity rover, equipped with a radiation detector, has measured these spikes. During one particularly intense solar event in 2017, radiation levels on Mars surged to more than double the normal daily dose within just a few hours. For a human on the surface, even inside a thin-walled habitat, such an event could cause acute radiation sickness. Nausea, vomiting, fatigue, damage to bone marrow and the gastrointestinal tract. Symptoms would appear within hours to days, depending on the dose received. Without medical intervention, a severe exposure could be fatal within weeks. Yet it is not the sudden, catastrophic events that pose the greatest danger to long-term Mars colonists. It is the slow, relentless accumulation of radiation over months and years. Chronic radiation exposure does not kill quickly. It degrades. It corrupts the delicate machinery of living cells, one particle at a time. Every high-energy particle that passes through human tissue has a small chance of striking a DNA molecule. Most of the time, the damage is repaired by cellular mechanisms refined over billions of years of evolution. But some damage goes unrepaired or is repaired incorrectly. Mutations accumulate. Over time, the risk of cancer grows. Studies of astronauts who have spent extended periods in space suggest that a mission to Mars, including the journey there and back plus surface time, could increase a person's lifetime cancer risk by anywhere from 5% to 20%, depending on solar activity and shielding effectiveness. For comparison, smoking a pack of cigarettes daily increases cancer risk by a similar margin. Living on Mars would be, biologically speaking, like choosing to become a chronic smoker, except the smoke is invisible, unavoidable, and originates from the cosmos itself. But cancer is not the only consequence. Recent research has revealed something more immediate and unsettling. Radiation affects the brain. High-energy particles, particularly galactic cosmic rays, can damage neurons and disrupt cognitive function. Studies on mice exposed to simulated space radiation show impaired memory, reduced spatial learning, and increased anxiety. Some particles create tiny tracts of damage through brain tissue, affecting neural pathways in ways that pharmaceutical drugs or therapy cannot easily reverse. Astronauts on Mars might find themselves struggling with decision-making, experiencing memory lapses, or suffering from mood disturbances, not from isolation or stress alone, but from the physical degradation of their neural architecture. This raises profound questions about the nature of survival. How do we measure a life's viability when not just the body, but the mind itself is under slow assault? What does it mean to survive on Mars if, after 5 years, your ability to think clearly has been compromised? These are not abstract philosophical concerns. They are practical challenges that any long-term Mars mission must address. Fortunately, Mars itself offers some answers hidden within its geology. While the planet lacks a global magnetic field and a thick atmosphere, it possesses something Earth does not: ancient lava tubes. These are vast underground tunnels carved billions of years ago when molten rock flowed beneath Mars's surface. Some of these tubes are enormous, large enough to contain entire cities. Satellite imagery and ground-penetrating radar have identified dozens of potential lava tube entrances, dark pits that descend into subterranean chambers shielded by tens or even hundreds of feet of rock. Rock is an excellent radiation barrier. Just a few meters of Martian regolith can reduce radiation exposure by half. Deep within a lava tube, radiation levels could drop to nearly Earth-like background levels. These natural structures could serve as ready-made habitats, requiring far less construction than surface domes while providing superior protection. Some scientists have suggested that if life still exists on Mars, it may have retreated into such shelters long ago, hiding beneath the surface where radiation cannot reach. Ice deposits, discovered in abundance beneath Mars's mid-latitudes, offer another form of shielding. Water and ice are effective at absorbing radiation. A habitat buried beneath several meters of Martian ice could provide significant protection while also serving as a resource for drinking water, oxygen production, and rocket fuel synthesis. The irony is striking. To survive on Mars, we may need to become subsurface dwellers, building our homes not atop the red plains under open skies, but within the planet's crust, surrounded by stone and ice. The question then becomes, how much radiation is acceptable? Space agencies are still debating this. Current NASA guidelines limit astronaut radiation exposure to levels that do not exceed a 3% increase in lifetime cancer risk. By that standard, a human could spend perhaps 300 to 500 days on Mars before reaching the limit. Yet these guidelines were developed for short missions, not permanent colonization. If humanity intends to live on Mars indefinitely, we must either accept higher risks or develop revolutionary shielding technologies, magnetic field generators, advanced materials that deflect particles, pharmaceuticals that enhance DNA repair. All of these are being explored, but none are yet proven at the scale required for planetary settlement. Radiation on Mars is not a problem that can be fully solved. It can only be managed, mitigated, endured. Unlike pressure or temperature, which can be controlled within a sealed environment, radiation is a force that permeates everything. It is the price of living on a world without a magnetosphere, the cost of abandoning the protective embrace of Earth's invisible shield. To survive on Mars is to accept that your body is under continuous siege, that every day adds another small increment to your lifetime risk, that the atoms within your cells are being struck, altered, slowly rewritten by particles that travelled across light years of space before finding their way into your bone marrow. This is the invisible killer. Not dramatic, not immediate, but patient and inevitable. Radiation does not care about your courage, your technology, or your dreams of becoming an interplanetary species. It simply exists, flowing through the Martian landscape like an ancient, indifferent tide. And yet, knowing all this, humans will still go. Because survival is not merely about avoiding death, it is about choosing which risks to accept in pursuit of something greater. On Mars, radiation is the price of admission to a new world. The question is not whether we can eliminate the danger, but whether we can live with it long enough to build something lasting beneath alien skies. Inside the walls of a basic Mars habitat, you have crossed the first threshold of survival. The 11-second countdown has become irrelevant. The desperate hours in a failing spacesuit are behind you. Here, enclosed within thin layers of reinforced fabric and metal, you have achieved something extraordinary. The ability to measure your survival, not in moments or hours, but in weeks, perhaps even months. Yet this achievement comes with a profound realization. The habitat is not salvation. It is a clock, and every system within it is counting down toward an inevitable end. A minimum viable habitat on Mars is a marvel of engineering compressed into fragile simplicity. Picture a structure no larger than a small house, perhaps a modified inflatable module, or a rigid cylindrical shell transported from Earth. Inside this space, you have perhaps 50 to 100 square meters of living area. The walls are layered with radiation shielding, thermal insulation, and structural reinforcement. Yet they remain desperately thin against the hostile Martian environment pressing in from all sides. Outside, the atmospheric pressure is less than 1% of Earth's. Inside, pressurized air pushes constantly against every seal, every joint, every potential weakness. This is not a home. This is a pressure vessel keeping you alive through the continuous application of technology against entropy. Your first concern is oxygen, the invisible currency of survival. Unlike the limited supply in a spacesuit tank, a habitat employs regenerative systems, technologies that extract breathable air from the very molecules around you. The most critical of these is an oxygen generation system, likely based on electrolysis, the process of splitting water molecules into hydrogen and oxygen using electricity. Water flows into the electrolysis unit. Electricity tears apart its molecular bonds, and oxygen flows into the habitat's atmosphere, while hydrogen is either vented or stored for other uses, perhaps as fuel or combined back into water later. This system is elegant in theory, but in practice, it is a lifeline balanced on the edge of failure. Every breath you take requires power. The solar panels outside, covered gradually by Martian dust, must generate enough electricity to continuously run the electrolysis system. If a dust storm darkens the sky for days or weeks, as they often do on Mars, battery reserves begin to drain. The backup fuel cells, if they exist, become your final buffer against suffocation. But these too are finite. In a basic habitat, there may be no redundancy. One electrolysis unit, one set of filters, one pathway between you and asphyxiation. When that system fails, and on Mars, all systems eventually fail, you will have hours to repair it before carbon dioxide levels rise to toxic concentrations and oxygen levels fall below the threshold of consciousness. Water presents its own cascade of challenges. Unlike Earth, where water falls from the sky and flows in rivers, Mars offers only frozen reserves buried beneath the regolith and trace amounts of atmospheric water vapor. Your habitat likely includes a water recycling system, a technological loop that captures every drop of moisture. Humidity from your breath condenses on collection surfaces. Urine flows into a distillation and filtration system. Even the water you use for washing, if you use any at all, cycles through purification and returns to your supply. The efficiency of these systems is extraordinary, often reclaiming 90% or more of water, but that missing 10% compounds over time. Week by week, your total water supply shrinks unless you can mine ice from the Martian surface, melt it, purify it, and replenish your stores. Mining water on Mars is not a simple task. It requires venturing outside in your spacesuit, drilling or excavating into frozen soil, transporting chunks of ice-laden regolith back to the habitat, and processing it through heating and filtration. Each excursion risks your spacesuit. Each heating cycle requires precious energy. And the water you extract may be contaminated with perchlorates and other chemicals that require additional purification steps. In a basic habitat, the question is not whether you can recycle water, but whether you can supplement your recycling faster than your supply degrades. Food, however, is where the timeline becomes brutally finite. A basic habitat does not have extensive agricultural systems. There are no fields of potatoes growing under LED lights, no hydroponics bays producing fresh vegetables. Instead, you have stored rations, freeze-dried meals, nutrition bars, packaged supplies brought from Earth. If you are fortunate, you might have enough food for 6 months, perhaps a year if rationed carefully. But eventually, the last package will be opened, the final meal will be consumed, and then, no matter how well your oxygen and water systems function, starvation begins its slow, inexorable countdown. The mathematics of food storage are unforgiving. An average person requires approximately 2,000 calories per day, though physical activity and environmental stress on Mars might increase that need. At 2,000 calories per day, a single person requires 730,000 calories per year. Freeze-dried food provides roughly 100 to 150 calories per ounce. That means you need approximately 5,000 ounces, or over 300 pounds of food per person per year. For a 6-month supply, you need 150 pounds of food, occupying significant volume within your already cramped habitat. When that supply runs out, no amount of ingenuity with oxygen or water will prevent your body from consuming itself. Yet perhaps the most insidious threat inside a basic habitat is not mechanical failure or resource depletion, but the slow erosion of the mind. Psychological isolation on Mars would be unlike anything experienced on Earth, more profound than solitary confinement, more complete than the loneliness of the open ocean. You are not merely alone, you're alone on another world, with no possibility of rescue, no chance of human contact, and the knowledge that every person you have ever known is separated from you by tens of millions of miles of cold vacuum. The sun rises and sets in muted ochre tones. The landscape outside your window never changes, an endless expanse of rust-coloured rocks stretching to horizons that seem close enough to touch, yet impossibly distant. Inside the habitat, the walls press in. The same surfaces surround you every day, The same recycled air fills your lungs. The same mechanical hums provide the only soundtrack to existence. Studies of isolation in Antarctic research stations and long-duration space missions reveal that humans are profoundly social creatures. Prolonged isolation leads to depression, anxiety, and cognitive decline. Decision-making becomes impaired. Judgment falters. Some individuals experience hallucinations or delusional thinking. On Mars, in a basic habitat with no communication delay shorter than several minutes each way, the psychological crisis would be acute and potentially fatal. Poor decisions born from isolation and stress could trigger cascades of failure. A moment of inattention while repairing the oxygen system could result in a critical mistake. Despair could lead to neglect of essential maintenance tasks. The slow accumulation of small errors could compound into catastrophic system failures. On Earth, we rely on others to catch our mistakes, to provide perspective, to intervene when we make poor choices. On Mars, alone inside a basic habitat, there is no safety net. Your mind is both your greatest asset and your most vulnerable single point of failure. Equipment failures, when they occur, create cascades that basic habitats are ill-equipped to handle. Consider a simple leak in the habitat's pressure seal. Martian dust, impossibly fine and electrostatically charged, works its way into the breach. The leak slowly worsens. You attempt to repair, but without proper materials or spare parts, the fix is temporary. Atmospheric pressure begins to drop. The oxygen generation system must work harder to compensate. Power consumption increases. Battery reserves drain faster. Soon, you are caught in a spiral where each problem amplifies the next, and your ability to respond diminishes with each passing day. In spacecraft and habitat design, engineers speak of single points of failure, components whose malfunction would result in total system loss. A basic habitat, by definition, is riddled with such vulnerabilities. One oxygen generator, one water recycling unit, one battery bank, one pressure shell. The failure of any critical component could mean the difference between survival and death. And in the harsh Martian environment, failures are not theoretical, they are inevitable. Dust clogs, filters, seals degrade, electronics fail under radiation exposure, mechanical parts wear out. The habitat does not break all at once. It erodes piece by piece, system by system, until the remaining functional components can no longer sustain life. Inside a basic habitat, survival is measured not just in resources, but in resilience. How long can you maintain vigilance? How long can you perform repairs with degrading tools? How long can your mind withstand isolation before critical errors occur? The timeline stretches from weeks to months, but the upper boundary is determined not by a single factor, but by the intersection of resource depletion, equipment failure, and psychological collapse. This is survival on Mars in its most fundamental form, not the dramatic 11-second death of vacuum exposure, but the slow, methodical consumption of everything that keeps you alive. The habitat is a shell of temporary safety in an environment that permits no mercy, no second chances, and no miracles. Inside these walls, you have bought yourself time. But time on Mars, like air and water and food, is a finite resource that cannot be renewed without support from Earth. And when that support is absent, the countdown continues, slower but no less certain, toward an ending written in the cold mathematics of survival itself. You have sealed yourself inside the habitat. The airlock has cycled. Your spacesuit hangs in the decontamination chamber. You breathe deeply, finally free from the confines of your helmet. The air tastes clean, filtered, processed through systems designed to mimic Earth's atmosphere. You begin to feel safe. But safety on Mars is an illusion that dust will quietly dismantle. Martian dust is not like the dirt beneath our feet on Earth. It is not soil weathered by rain and shaped by life. It is regolith, ancient and alien, forged through billions of years of meteor impacts, volcanic eruptions, and oxidation processes that have transformed the surface into something fundamentally hostile to human biology. Under a microscope, Martian dust reveals itself as a collection of jagged particles, each grain sharp as broken glass, smaller than particles of talcum powder, capable of penetrating filters, seals, and eventually human tissue. The composition is what makes it truly dangerous. Iron oxide gives Mars its rust-red color, but embedded within that familiar hue is something far more insidious: perchlorates. These chlorine compounds, discovered by NASA's Phoenix lander in 2008 and confirmed by multiple subsequent missions, exist throughout the Martian surface at concentrations of approximately 0.5% to 1% by weight. This may sound negligible, but in the context of human survival, it is catastrophic. Perchlorates are thyroid disruptors. Once inside the human body, they interfere with iodine uptake, blocking the thyroid gland's ability to produce essential hormones that regulate metabolism, energy production, and countless cellular functions. Exposure does not kill immediately. Instead, it initiates a slow cascade of biological failure. Fatigue sets in first, subtle and easy to dismiss. Then cognitive impairment follows, memory problems, difficulty concentrating, the fog of hypothyroidism descending like a veil over consciousness. Left unchecked, perchlorate poisoning leads to severe metabolic dysfunction, cardiovascular complications, and in pregnant individuals, catastrophic developmental harm to fetuses. The challenge is not simply avoiding the dust. The challenge is that avoiding the dust is fundamentally impossible. Every time an astronaut returns from the Martian surface, they carry dust with them. The finest particles, those measuring less than 20 microns in diameter, cling to spacesuits with tenacity that defies conventional cleaning methods. On Earth, dust settles. Gravity and moisture cause particles to clump together and fall. But Mars is different. Its gravity is only 38% of Earth's, and its atmosphere is extraordinarily dry, with humidity levels near zero. This creates conditions where dust does not settle. It hovers, it drifts, it finds its way into every microscopic gap, every seal, every junction between components. Static electricity transforms the problem from difficult to nearly insurmountable. Without moisture in the atmosphere to dissipate electrical charge, Martian dust becomes electrostatically active, clinging to surfaces with forces that exceed simple mechanical adhesion. During the Apollo missions to the Moon, astronauts discovered that lunar dust, which shares similar properties, proved impossible to fully remove. It infiltrated habitats despite rigorous cleaning protocols. It damaged equipment. It was inhaled, tasted, felt in every corner of the enclosed environment. Martian dust will behave the same way, only worse, because Mars has global dust storms that can blanket the entire planet for months, filling the thin atmosphere with particles that fall back to the surface slowly, covering every exposed object in a fine, toxic layer. Inside your habitat, filtration systems work continuously, pulling air through HEPA filters designed to capture particles down to 0.3 microns. But Martian dust includes particles far smaller, nanoparticles that slip through conventional filters like ghosts through walls. With every airlock cycle, with every depressurization and repressurization, microscopic amounts of dust enter the living space. Over weeks and months, concentrations build. What begins as trace contamination becomes measurable exposure. The respiratory impact extends beyond chemical toxicity. The physical structure of Martian dust particles inflicts mechanical damage on lung tissue. Their sharp, angular shapes, never smoothed by wind or water erosion, act like microscopic shards of glass when inhaled. They lodge in the deepest recesses of the lungs, the alveoli where oxygen exchange occurs, causing inflammation and scarring. This is not unlike the effects of silicosis, the deadly lung disease that plagued miners throughout history, except with the added burden of chemical toxicity from perchlorates and reactive iron compounds. Some researchers have suggested that Martian dust may also contain reactive oxidants, substances that were first theorized following the Viking lander experiments in the 1970s. These oxidants, if they exist, would attack organic molecules on contact, potentially damaging cellular membranes and proteins. The evidence remains uncertain, debated within the scientific community, but the possibility adds another layer of concern. We are planning to send humans to a world where even the dust might be chemically aggressive toward life itself. Long-term accumulation in the body presents a timeline of deterioration that is difficult to predict with precision. Animal studies using perchlorate-contaminated water have shown effects at surprisingly low doses, particularly on neurological development and thyroid function. Extrapolating to human exposure on Mars, where inhalation and dermal contact would occur daily despite precautions, suggests that chronic health impacts could manifest within months. Mitigation through iodine supplementation offers some protection, helping the thyroid compete with perchlorates for uptake, but it is not a complete solution. The mechanical damage to lungs, the inflammatory responses, the potential for oxidative stress, these cannot be easily countered with supplements or medication. Engineers have proposed numerous strategies for managing the dust problem. Advanced airlock designs featuring multiple cleaning stages, electrostatic dust removal systems, even proposals for leaving spacesuits permanently outside the habitat, access through specialized ports that allow astronauts to enter from behind without bringing the suit into living spaces. Each approach offers incremental improvement, yet none provides complete protection. Some have imagined constructing habitats underground or within lava tubes, natural caves formed by ancient volcanic activity. This would reduce exposure to surface dust and provide additional radiation shielding, addressing multiple threats simultaneously. But excavation or modification of these spaces would stir up centuries of accumulated dust, creating hazardous conditions during construction. The dust problem follows us wherever we go on Mars, an invisible adversary that cannot be negotiated with or defeated, only managed and endured. Perhaps the most unsettling aspect of the dust hazard is its subtlety. Radiation announces itself through dosimeters and calculations. Pressure loss triggers alarms. But dust accumulates silently, particle by particle, breath by breath. By the time symptoms appear, damage has already begun. The thyroid has been compromised. The lungs have begun to scar. The body's natural repair mechanisms, evolved over millions of years on Earth, face a challenge they were never designed to meet. Future missions may develop advanced nanotechnology-based filtration, genetically modified lung tissue more resistant to particulate damage, or pharmaceutical interventions that counteract perchlorate absorption more effectively than iodine alone. But these solutions remain hypothetical, years or decades away from practical implementation. The astronauts of the first Mars missions will face the dust as it is, armed only with the imperfect tools we can provide them today. This is not a reason to abandon the dream of Mars, but it is a stark reminder that survival there is not simply about oxygen and water and temperature. It is about defending the human body against an environment that is toxic at the molecular level. Every grain of Martian dust carries within it the story of a dead world, and that story, beautiful and tragic, is one that human biology was never meant to read. The clock continues to count. With each passing day inside your habitat, the dust finds its way closer, settling into corners, coating surfaces, entering lungs with every breath. This is the price of living on Mars, paid not in dramatic moments of crisis, but in the slow, steady accumulation of something so small it cannot be seen with the naked eye, yet powerful enough to end survival one particle at a time. Now we venture beyond mere survival into something more profound: endurance. With resupply missions arriving from Earth, the question shifts from how long can you last to how long can your body withstand Mars itself? This is where survival transforms from days into years, but it is also where we encounter a darker truth. Mars does not kill you quickly with regular supplies. Instead, it dismantles you slowly, methodically, reshaping your biology one day at a time until the human body becomes something subtly alien. NASA's current projections for Mars missions anticipate crew survival periods of approximately 500 to 1,000 days, roughly 16 to 33 months, assuming regular resupply missions maintain a steady flow of essentials. This is not optimism. This is calculated reality based on current technology and our understanding of human physiology under extreme conditions. With oxygen generators functioning, water recycling systems operational, and food arriving on schedule, the immediate threats, suffocation, dehydration, starvation, fade into the background. What emerges in their place is something far more insidious: the accumulated degradation of the human body, exposed to an environment it was never designed to inhabit. Regular resupply missions would need to deliver more than simple consumables. Each cargo shipment would carry a carefully calculated manifest of survival essentials. Fresh food supplies to supplement whatever can be grown locally. Replacement parts for life support systems, because on Mars, a broken valve or malfunctioning filter is not an inconvenience, it is a death sentence. Medical supplies including antibiotics, surgical equipment, and radiation countermeasures. Spare spacesuits, because the Martian dust degrades seals and joints with relentless efficiency. Batteries and power generation components. Communication equipment. Psychological support materials, books, entertainment, anything to maintain mental health in an environment of absolute isolation. Each resupply mission is not just a delivery. It is a lifeline stretched across 140 million miles of void. But here we encounter one of Mars exploration's most frustrating constraints: the launch window problem. Earth and Mars align favorably for spacecraft transit only once every 26 months. This celestial rhythm is dictated by orbital mechanics, an unchangeable fact of physics. It means that if a critical component fails, if a crew member suffers a medical emergency requiring equipment not currently available, If food supplies run shorter than anticipated, there is no emergency shipment arriving next week. There is only waiting. 26 months is not merely a scheduling inconvenience. It is a chasm of vulnerability, during which anything that goes wrong must be solved with whatever resources are already on Mars. This waiting period transforms every supply calculation into a high-stakes gamble. Every backup system becomes a temporary reprieve rather than a permanent solution. Consider the mathematics of survival across multiple resupply cycles. A crew arrives with enough supplies for 18 months. 6 months after landing, the first resupply mission arrives, replenishing stocks and extending survival to another 18 months. But launches are expensive, payloads are limited, and each shipment must be planned years in advance. If one launch fails, if one cargo ship experiences a catastrophic malfunction during the 7-month journey to Mars, the entire timeline collapses. The crew suddenly faces rationing, difficult decisions, and the very real possibility that the next launch window arrives too late. Mars rewards meticulous planning, but it punishes even the smallest miscalculation with absolute finality. Yet even with perfect resupply logistics, even if every shipment arrives exactly on schedule with every item intact, the human body begins to fail. This is the truth that NASA's mission planners study with quiet concern. Mars itself is toxic to human physiology, not through any single catastrophic mechanism, but through the slow accumulation of changes that compound month after month, year after year. Bone density loss occurs at a rate of approximately 1 to 2% per month in Mars's reduced gravity. Earth's gravity constantly stresses our skeletal system, triggering bone cells to rebuild and strengthen. On Mars, with only 38% of Earth's gravitational pull, this stress disappears. The body interprets the reduced load as a signal that dense, heavy bones are no longer necessary. Calcium begins leaching from the skeleton into the bloodstream, expelled through urine in concentrations that increase the risk of kidney stones. After 1 year on Mars, an astronaut could lose 12 to 24% of their bone density. After 2 years, 24 to 48%. At a certain point, bones become so fragile that a simple fall, a momentary loss of balance, results in fractures. The skeleton that once supported your weight becomes a brittle framework insufficient for the demands of physical work. Muscle atrophy follows a similar trajectory. Without Earth's constant gravitational resistance, muscles begin to waste. Even with rigorous daily exercise, studies on the International Space Station have shown muscle mass decreases by 20% over 6 months. On Mars, the effect is somewhat lessened by the partial gravity, but it is not eliminated. The heart, a muscle itself, begins to shrink. Cardiovascular capacity declines. The body that could once run, lift, and endure becomes weaker, slower, more vulnerable to injury and exhaustion. After years on Mars, astronauts might find themselves capable of functioning in Martian gravity, but completely unable to survive a return to Earth's stronger pull. Vision changes present an unexpected horror. In reduced gravity and altered atmospheric pressure, fluid distribution throughout the body shifts. On Earth, gravity pulls fluids downward. On Mars, fluids migrate toward the head, increasing intracranial pressure. This pressure compresses the optic nerve and deforms the eyeball itself, causing a condition observed in many astronauts called spaceflight-associated neuroocular syndrome. Vision becomes blurred. Some astronauts develop permanent changes to their eyesight, requiring corrective lenses they never needed before. In severe cases, the changes are irreversible. After years on Mars, returning astronauts might see the world through permanently altered eyes, a physical reminder that their bodies have been fundamentally reshaped by time spent beyond Earth. Radiation exposure accumulates silently. Even inside a habitat with radiation shielding, astronauts receive doses far exceeding Earth normal background levels. Mars has no magnetic field and only a thin atmosphere to deflect cosmic rays and solar radiation. Over months and years, this exposure damages DNA, increases cancer risk, and may accelerate aging at the cellular level. Current estimates suggest that after 500 days on Mars, an astronaut would receive a lifetime's maximum recommended radiation dose. Beyond that threshold, every additional day increases the probability of long-term health consequences. Cancer that develops years after return, neurological damage that manifests slowly, genetic mutations that might affect future generations. Then there is the point of no return, a concept both literal and metaphorical. Physically, it is the moment when an astronaut's body has changed so dramatically that returning to Earth's gravity would be medically catastrophic. Bones too fragile to support full weight, heart too weakened to pump blood against stronger gravity, muscles too atrophied to function. This threshold likely occurs somewhere between 3 to 5 years of continuous Mars habitation, though individual variation makes precise prediction impossible. Beyond this point, Mars becomes not a temporary assignment, but a permanent home, not by choice, but by biological inevitability. Psychologically, there is also a point of no return. After years of isolation, living in confined habitats, breathing recycled air, eating limited food varieties, viewing Earth as nothing more than a distant blue star, the human mind adapts. Some astronauts might find they no longer feel connected to Earth's humanity. The concerns of people living under open skies, with unlimited horizons and abundant resources, become incomprehensible. Mars becomes home, not because it is welcoming, but because it is all that remains familiar. The psychological transformation mirrors the physical one, a slow reshaping of identity until the person who returns to Earth is not quite the same person who left. NASA's survival projections account for these factors. The 500 to 1,000 day mission timelines are not arbitrary. They represent the window during which astronauts can survive, maintain functionality, and crucially, return home with bodies still capable of readapting to Earth. Push beyond this window, and you venture into unknown territory where survival is possible, but recovery may not be. With resupply missions, you can survive on Mars for years, but survival and thriving are not the same. Each passing month trades immediate existence for long-term health. Each resupply shipment extends the timeline, but cannot halt the body's slow transformation. Mars offers years of life, but it demands payment in bone, muscle, vision, and cellular integrity. The question is not whether you can survive for years on Mars with regular supplies. The question is whether, after those years, you would still recognize the body you inhabit, and whether Earth would still recognize you. In the silence of a Martian habitat, a single potato plant pushes through treated soil. Its leaves unfurl slowly under artificial light, drawing energy from photons that have traveled 140 million miles, filtered through transparent aluminum, converted to wavelengths optimized for chlorophyll absorption. This is not just agriculture. This is the transformation of survival from a countdown into a future. Growing food on Mars is not a convenience. It is the dividing line between temporary existence and permanent settlement, between watching the clock run down and building a world that sustains itself. The idea captured our imagination through fiction. Mark Watney, stranded on Mars, cultivating potatoes in regolith fertilized with human waste, extending his survival against impossible odds. It made for compelling cinema. But the reality of Martian agriculture is far more complex, far more challenging, and paradoxically, far more achievable than Hollywood suggested. The question is not whether we can grow food on Mars. The question is what it truly takes to turn a dead planet's surface into something that can nourish human life. Mars presents a unique agricultural challenge. The regolith beneath our feet contains many of the mineral nutrients that plants require: nitrogen, phosphorus, potassium, iron, magnesium. Chemical analysis reveals that Martian soil is not entirely alien to plant life, yet it is also hostile in ways that go beyond simple chemistry. The soil contains perchlorates, toxic compounds that would poison any plant attempting to draw water from untreated regolith. Before a single seed can be planted, the soil must be remediated, washed repeatedly with water that itself is precious, processed through systems that filter out the compounds that would kill both plants and humans. This is not gardening. This is planetary decontamination at the microscopic level. The process of soil remediation takes time, energy, and resources that a struggling colony can barely afford. Water must be heated, cycled through the regolith, filtered, tested, and recycled. Each kilogram of soil prepared for cultivation requires liters of water and hours of processing. And even after remediation, the soil lacks something essential: organic matter. Earth soil is alive, teeming with bacteria, fungi, decomposers that break down organic material and make nutrients available to plant roots. Martian regolith is sterile, dead for billions of years. To make it truly fertile, we must not just clean it, we must resurrect it, introducing Earth microorganisms that can survive in this alien environment, creating an ecosystem from nothing. The experiments have already begun. Here on Earth, scientists cultivate crops in simulated Martian regolith, testing which plants can tolerate the chemical composition, which varieties produce the highest caloric yield per square meter. Potatoes emerge as a candidate not because of fiction, but because of mathematics. A single potato plant can produce several pounds of tubers, rich in carbohydrates, requiring relatively modest amounts of water compared to grains like wheat or rice. But potatoes alone cannot sustain human life. They lack complete proteins, essential amino acids, vitamin B12, and numerous micronutrients that prevent deficiency diseases. The menu on Mars must be diverse, carefully calculated to provide not just calories, but complete nutrition. This is where the calorie mathematics becomes stark and unforgiving. An adult human requires approximately 2,000 to 2,500 calories per day, more if engaged in the physical labor that Martian colonization demands. Growing that much food requires space, energy, and water on a scale that challenges our engineering capabilities. A single person might require 50 to 80 square meters of growing space to produce sufficient food, assuming optimal conditions, no crop failures, and varieties specifically selected for maximum yield. Multiply that by a crew of 6, and suddenly we need a greenhouse the size of a tennis court, hermetically sealed, pressurized, heated, and illuminated continuously. The energy demands are extraordinary. Plants on Earth receive sunlight filtered through an atmosphere, distributed across wavelengths that chlorophyll has evolved to capture efficiently. On Mars, even inside a greenhouse, light levels are 40% lower than on Earth due to distance from the sun. Supplemental lighting becomes not optional, but essential. LED arrays optimized for photosynthesis must run for 16 to 18 hours per day, consuming kilowatts of electricity that must be generated by solar panels or nuclear reactors, both of which require maintenance, both of which can fail. The energy cost of growing food on Mars rivals the energy cost of maintaining the habitat itself. Water presents its own labyrinth of challenges. Plants transpire, releasing water vapor into the air through their leaves. In a closed greenhouse environment, this moisture must be captured, condensed, purified, and returned to the irrigation system. Nothing can be wasted. Yet plants also incorporate water into their tissues, into the fruits and vegetables they produce, water that is temporarily removed from the recycling system when food is harvested and consumed. The water budget must account for every molecule, balancing extraction from Martian ice, electrolysis of water for oxygen production, crew consumption, and agricultural needs. A single miscalculation, a single system failure, and the delicate balance collapses. Then there is the question of pollination, a process so commonplace on Earth that we rarely consider its complexity. Many crops require pollination to produce fruit: tomatoes, peppers, squash, beans. On Earth, insects, wind, and gravity facilitate this exchange of pollen. On Mars, in a sealed greenhouse with controlled atmosphere and minimal air movement, pollination becomes a manual task. Human hands must mimic the work of bees, transferring pollen from flower to flower with brushes or vibrating tools, a labor-intensive process that cannot be neglected without sacrificing the harvest entirely. Some scientists propose introducing bees or bumblebees to Martian greenhouses, creating a miniature Earth ecosystem. But bees require their own food sources, their own environmental controls, their own care. We would be sustaining not just plants, but an entire web of life in a habitat surrounded by death. The challenges extend beyond mechanics into biology itself. Plants evolved under Earth's gravity, Earth's atmospheric pressure, Earth's day-night cycle. Mars rotates on a similar schedule, 24 hours and 37 minutes, close enough that circadian rhythms remain intact. But gravity is 38% of Earth's, and this affects how water moves through plant tissues, how roots anchor themselves, how stems support leaves and fruit. Early experiments suggest most plants adapt, but yields may be lower, growth rates slower, structural integrity compromised. We're asking Earth life to thrive in conditions it has never encountered across millions of years of evolution. Nutrient deficiencies present a silent, creeping danger. Even if we grow potatoes, lettuce, tomatoes, and beans, we face gaps in the nutritional profile. Vitamin B12, found primarily in animal products, cannot be synthesized by plants. Without supplementation, colonists would develop pernicious anemia, neurological damage, irreversible harm. Omega-3 fatty acids, calcium in sufficient quantities, certain trace minerals, all require careful planning, fortification, or supplementation from Earth. A Martian diet might keep you alive, but malnutrition can be subtle, manifesting over months or years in weakened bones, compromised immune systems, cognitive decline. The fiction of Mark Watney's potatoes while inspiring, glossed over these realities. In the story, potatoes grew in days, fertilized with human waste applied directly to soil with minimal processing. In reality, human waste requires extensive composting, heat treatment to kill pathogens, careful monitoring to prevent contamination with bacteria that could devastate both crops and crew. The time frame for establishing a productive garden is not days, but months. The first harvest comes not when you plant seeds, but when you have prepared the soil, tested the systems, ensured redundancy, and watched carefully as the first fragile leaves emerge, hoping nothing goes wrong. Yet despite these challenges, growing food on Mars is not impossible. It is merely difficult, demanding, and absolutely essential. Every calorie produced on Mars is a calorie that doesn't need to be launched from Earth at costs measured in thousands of dollars per kilogram. Every successful harvest extends the timeline from months of survival to years, from years to decades. Agriculture on Mars is the game changer because it transforms colonists from consumers of dwindling resources into producers of renewable sustenance. It is the moment when survival stops being a countdown and becomes, instead, a cycle. In the end, the Martian greenhouse is not just a structure. It is an act of defiance against a dead world. It is the insistence that life, given the right conditions, the right care, and the right determination, can take root anywhere. Even here, beneath a pink sky, in soil that has known no rain for billions of years, a plant grows. And with it, so does the possibility of permanence. You have survived the radiation. You have conquered the dust. You have grown food in alien soil and breathed recycled air for months, perhaps years. But then, in the middle of a Martian night, you wake with a pain in your abdomen, sharp, insistent, growing. On Earth, this would be an inconvenience, a trip to the emergency room, a routine surgery. On Mars, 140 million miles from the nearest hospital, this pain could be your death sentence. Medical emergencies on Mars are not just complications. They are existential crises. Every symptom becomes a countdown. Every diagnosis becomes a gamble with time itself. Here, in the thin atmosphere of the red planet, the human body does not simply fall ill. It confronts the terrifying reality that modern medicine, with all its miracles, may be powerless to save you. Consider appendicitis, one of the most common surgical emergencies on Earth. Roughly 1 in 15 people will experience it in their lifetime. The appendix, a small finger-shaped organ attached to the large intestine, becomes inflamed and infected. Without treatment, it ruptures, spilling bacteria throughout the abdominal cavity, leading to peritonitis, sepsis, and death. On Earth, appendicitis is alarming but manageable. Emergency surgery is routine, performed thousands of times daily in hospitals around the world. The survival rate exceeds 99%. On Mars, appendicitis is catastrophic. The first challenge is diagnosis. Medical imaging on Mars would be limited. A full hospital's worth of equipment cannot be transported across interplanetary space. CT scanners, MRI machines, ultrasound devices, each weighs hundreds or thousands of pounds and requires power, maintenance, and expertise. Even with diagnostic tools, the symptoms of appendicitis can mimic other conditions: bowel obstructions, kidney stones, even muscle strain from working in a spacesuit. Misdiagnosis wastes precious hours. Every hour of delay increases the risk of rupture exponentially. If appendicitis is confirmed, surgery becomes necessary. But surgery on Mars is not surgery on Earth. The operating environment is fundamentally different. Mars has only 38% of Earth's gravity. In low gravity, blood does not pool and flow as it does under terrestrial conditions. During an incision, blood can float, forming spherical droplets that drift through the air, obscuring the surgical field and contaminating instruments. Surgeons would need to work within enclosed systems, using suction devices continuously, adapting techniques developed for zero-gravity environments aboard space stations. Then there is the issue of anesthesia. General anesthesia requires careful monitoring of breathing, heart rate, and blood pressure. But the human body behaves differently in low gravity. Fluids shift toward the upper body, altering cardiovascular dynamics. Anesthetic drugs may metabolize unpredictably. Dosing becomes guesswork. Too little, and the patient wakes during surgery. Too much, and respiratory failure follows. There is no anesthesiologist on call, no backup team, no trauma center down the hall if something goes wrong. Even if the surgery succeeds, recovery is perilous. Wound healing in low gravity is slower. The body's immune response is compromised by radiation exposure and the stress of living in an artificial environment. Infections that would be minor annoyances on Earth become life-threatening. Antibiotics are essential, but here lies another silent killer: medication degradation. Pharmaceuticals are not designed for interplanetary travel. Radiation bombards everything on Mars: cosmic rays and solar particles that penetrate habitats and storage containers. This radiation breaks down chemical compounds, rendering medications less effective or even toxic. Studies of drugs stored aboard the International Space Station have shown accelerated degradation. Aspirin loses potency. Antibiotics become unstable. Insulin breaks down. On Mars, the very medicines meant to save lives may quietly become useless. Imagine developing a severe bacterial infection. On Earth, a course of antibiotics resolves it within days. On Mars, you open the medical supply cabinet and inject what you hope is a functional antibiotic. But the drug has been stored for 18 months. Radiation has altered its molecular structure. You inject it, and nothing happens. The infection spreads, fever climbs, sepsis begins. There is no pharmacy to call, no emergency shipment, no alternative. You can only wait and watch and hope. Dental emergencies may seem trivial compared to appendicitis, but on Mars, a toothache can spiral into a nightmare. A cracked tooth, a deep cavity, an abscess forming in the jaw. These are not merely painful. They are gateways to systemic infection. Bacteria from dental abscesses can enter the bloodstream, traveling to the heart, the brain, the lungs. Without a dentist, without proper dental instruments, treatment options are medieval. Extraction with improvised tools, pain management with degraded medications, infection control with limited antibiotics. An abscess that remains untreated will continue to grow. The infection spreads through the tissues of the face and neck. Swelling can obstruct the airway. Sepsis follows. Death comes not from the tooth itself, but from the body's inability to contain the infection it harbors. On Earth, this is preventable. On Mars, it is a slow, agonizing countdown. And then there is the invisible epidemic that no amount of preparation can fully prevent: mental health crises. Mars is isolating beyond comprehension. You are confined to a small habitat with a handful of people, breathing recycled air, eating the same meals, watching the same rust-colored landscape day after day. Communication with Earth is delayed by up to 22 minutes each way. Conversations become asynchronous. Real-time support is impossible. You are alone in a way that no human has ever been alone. Depression, anxiety, psychosis. These are not abstract possibilities. They are statistical certainties in prolonged isolation. Studies of Antarctic research stations, submarines, and space missions reveal patterns of psychological breakdown. Crew members experience mood swings, insomnia, paranoia, and in extreme cases, suicidal ideation. On Earth, a mental health crisis can be managed with therapy, medication adjustments, and if necessary, evacuation to a treatment facility. On Mars, there is no evacuation. There is no psychiatric hospital. There is no option to leave. If a crew member becomes violent, endangering themselves or others, the responses are limited and grim. Sedation with degraded medications, physical restraint, isolation within an already isolated world. The ethics become unbearable. Do you sedate someone indefinitely? Do you lock them away? Do you risk the safety of the entire crew to preserve the dignity of one person in crisis? And what if the crisis is your own? What if you are the one who begins to unravel, feeling the weight of distance press upon your mind, watching your thoughts twist into patterns you no longer recognize? There is no therapy session scheduled for next week. There is no comforting voice telling you it will be okay. There is only the hum of life support systems, the silence of the Martian wind, and the knowledge that you must endure. Medical triage on Mars forces impossible decisions. With limited supplies, limited expertise, and no hope of reinforcement, every resource must be rationed. If two people fall ill simultaneously, who receives treatment first? The engineer who maintains the life support systems, the biologist who manages the food supply, the pilot who might one day fly everyone home. These are not hypothetical dilemmas. They are the cold calculus of survival 140 million miles from help. In traditional medical ethics, the principle of do no harm guides every decision. On Mars, harm is inevitable. Every choice involves sacrifice. Every treatment plan is a negotiation with scarcity. To allocate antibiotics to one person is to deny them to another. To perform surgery is to risk contaminating the sterile field in ways that could endanger future patients. There are no easy answers, only questions that haunt the quiet hours when the dust storms subside and the stars burn cold above the frozen desert. The medical nightmare of Mars is not a single catastrophic event. It is the accumulation of vulnerabilities, each small and manageable on Earth, each lethal in isolation, a broken bone that does not heal correctly, a viral infection that spreads through the crew, a medication that has lost its potency, a mental breakdown that no one is trained to address. On Mars, your body is not just a vessel for life. It is a liability, a fragile biological system operating at the edge of its tolerances, held together by hope, improvisation, and the desperate ingenuity of people who know that help will never arrive in time. Here, survival is not just about enduring the environment. It is about enduring yourself. We have journeyed through survival measured in seconds, then hours, then months. But what if the question is not how long you can survive on Mars, but how long humanity itself could endure there? What would it take to build not a temporary outpost, but a civilization? To transform survival into permanence is to cross a threshold from which there may be no return. It is to acknowledge that Mars is no longer just a destination, but a home. The longest survival on Mars is not measured in the lifetime of a single human being. It is measured in generations, in the transformation of red dust into gardens, in children born beneath rust-coloured skies who will never breathe Earth's air. This is survival not as endurance, but as evolution. And it requires technology, infrastructure, and vision that stretches beyond anything humanity has ever attempted. Permanent habitation begins not on the surface, but beneath it. The Martian landscape is scarred by radiation, scoured by dust storms, and exposed to temperature swings that would shatter surface structures over time. The solution lies in descending into the planet itself. Mars is riddled with lava tubes, vast underground tunnels carved billions of years ago, when volcanic activity still surged beneath the planet's crust. These natural caverns, some wide enough to contain entire city blocks, offer protection that no surface habitat could match. Radiation is absorbed by meters of rock overhead. Temperature remains relatively stable. The threat of micrometeorites and dust storms vanishes entirely. To build underground is to embrace the geology of Mars as an ally. Using robotic excavators and 3D printing technology, tunnels could be expanded, reinforced, and transformed into multi-level habitats. Imagine corridors carved into ancient basalt, lined with pressurized modules that house laboratories, hydroponic farms, living quarters, and manufacturing facilities. Natural skylights could be engineered to pipe sunlight deep into the tunnels using fiber optics, bringing warmth and light to spaces that have known only darkness for eons. The first true Martian cities would not rise toward the sky. They would burrow into the bones of the planet. But even a perfect shelter is not enough. A self-sustaining biosphere must be created, a closed-loop system where nothing is wasted and everything is recycled. On Earth, nature performs this task effortlessly. On Mars, humans must become the architects of their own ecosystem. Water must be extracted from ice deposits, purified, and cycled through life support systems with near-perfect efficiency. Oxygen must be generated from the Martian atmosphere, which is 95% carbon dioxide, using chemical reactions that split molecules apart and recombine them into breathable air. The MOXIE experiment aboard NASA's Perseverance rover has already proven this is possible, but scaling it to support thousands of people requires industrial-level infrastructure that does not yet exist. Food production would anchor the entire colony. Unlike resupply missions that arrive every 2 years, a permanent settlement needs continuous harvests. Hydroponic and aeroponic farms would fill underground chambers, cultivating crops engineered to thrive in low light and Martian-enriched soil. Potatoes, wheat, soybeans, algae, each selected not just for nutrition, but for their ability to regenerate the atmosphere by consuming carbon dioxide and producing oxygen. Some scientists propose introducing genetically modified organisms, bacteria, and fungi designed to break down Martian regolith into usable soil, accelerating the process of terraforming from within the tunnels themselves. These are not simple farms. They are living engines of survival, transforming the sterile into the fertile. Yet agriculture alone cannot sustain a civilization. True independence requires industrial capacity. The ability to manufacture tools, repair equipment, and fabricate replacement parts without relying on Earth. Mars has abundant resources: iron oxide in the soil, silica for glass, sulfur compounds for chemistry, but extracting and refining them demands energy. Solar panels lose efficiency in the dust-filled atmosphere. Nuclear reactors become essential, small modular systems that can operate for decades, providing steady power to mining operations, factories, and life support systems. Without this energy infrastructure, a Martian colony remains dependent, vulnerable to the severing of the supply line from Earth. And then, there is the question that few discuss openly but everyone understands. Genetic diversity. A permanent population cannot be sustained by a handful of settlers. Biology demands a minimum viable population to avoid inbreeding and genetic bottlenecks. Studies suggest that at least 500 individuals, possibly several thousand, would be required to establish a genetically healthy, self-sustaining human population on another planet. These settlers would need to represent diverse genetic backgrounds, varied skill sets, and the psychological resilience to endure isolation, not for years, but for lifetimes. Some would be engineers and doctors. Others would be artists, teachers, and philosophers. A civilization is not built by technicians alone. It is built by people who can imagine a future worth living. Children born on Mars would face challenges we can only begin to understand. Growing up in 1/3 Earth gravity would alter their bone density, muscle development, and cardiovascular systems. They might grow taller, their bodies adapting to the lighter gravitational pull, but returning to Earth could become physically impossible. Their hearts, lungs, and skeletal structures would be optimized for Mars, not the home planet their parents left behind. In this sense, Martian colonization is not reversible. It is a one-way transformation, not just of a planet, but of the human species itself. The technology required for permanent habitation is staggering, and much of it does not yet exist. We can simulate it, theorize about it, even prototype small-scale versions, but the leap from experiment to implementation is vast. Advanced AI systems would need to manage life support autonomously, detecting failures before they become catastrophic. Medical facilities would require telemedicine links to Earth, but with communication delays of up to 22 minutes. Doctors on Mars would often operate without guidance, relying on robotics and AI-assisted surgery for conditions that would be routine on Earth. Psychological support systems would need to address isolation, depression, and the existential weight of living 140 million miles from home. Mental health would be as critical as physical health, perhaps more so. Some researchers propose that true permanence requires not just habitation, but transformation. The long-term goal, debated among scientists and ethicists alike, is terraforming, altering Mars's atmosphere, temperature, and surface conditions to make it more Earth-like. This would take centuries, perhaps millennia. It would involve releasing greenhouse gases to warm the planet, melting polar ice caps to create liquid water, and introducing photosynthetic organisms to generate oxygen. Whether such a project is ethical or even feasible remains uncertain. Mars has its own history, its own geological story written in stone and dust. To rewrite it entirely is to play a role we have never assumed before, not explorers or settlers, but planetary architects. The realistic timeline for a true Martian civilization is not decades, but centuries. The first crewed missions might arrive in the 2030s or 2040s. A small research base could be established by mid-century, but a self-sustaining colony, one that no longer depends on Earth for survival, would likely not emerge until the 2100s at the earliest. And a thriving, multi-generational civilization, one with its own culture, governance, and identity, might not fully mature until the 2200s or beyond. This is not a project for a single lifetime. It is a project for the species, yet the promise remains irresistible. To build permanent habitation on Mars is to ensure that humanity is no longer confined to a single world. It is to create a backup for civilization, a safeguard against extinction. If Earth were struck by an asteroid, ravaged by climate catastrophe, or torn apart by conflict, Mars could endure. Not as a refuge for the privileged, but as a continuation of the human story, written in a new landscape under alien skies. The longest survival on Mars is not about outlasting danger. It is about transcending it. It is about transforming a barren world into a living one, not through domination, but through adaptation, patience, and an understanding that permanence is not given. It is built, stone by stone, generation by generation, until Mars is no longer a foreign land, but a home. As we stand at the end of this journey through Mars survival, we must pause and absorb the stark arithmetic of existence on another world. The timeline we have traced is not a single path, but a spectrum, one that stretches from the fragile 11 seconds of unprotected exposure to the generational permanence of self-sustaining colonies. Between these extremes lies the truth that science fiction rarely acknowledges. Survival on Mars is not a matter of courage or determination alone. It is a battle against time itself, measured in heartbeats, oxygen reserves, and the slow accumulation of radiation damage that cannot be reversed. Without a spacesuit, you have mere seconds. With one, perhaps hours or days before critical systems fail. Inside a basic habitat, weeks stretch into months, but only if nothing breaks, only if resupply arrives on schedule, only if the red dust does not find its way into your lungs and bloodstream. With regular resupply missions and advanced technology, years become possible. With greenhouses producing food and closed-loop life support systems, decades may unfold. And with permanent infrastructure, underground cities carved into ancient lava tubes, magnetic shields deflecting cosmic radiation, industrial capacity to manufacture replacement parts, Mars could become home to generations who will never see Earth except as a pale blue star in their night sky. Yet here is the sobering reality. We are not there yet. The gap between our current capabilities and what Mars demands is vast. We have sent rovers that last years, but no machine we have built could sustain a single human for even one Martian year without constant support from Earth. The technology being developed today, advanced radiation shielding, in situ resource utilization systems that extract water from Martian ice, nuclear reactors designed to function in thin atmosphere, medical AI capable of performing surgeries remotely. These are not luxuries. They are absolute necessities. Without them, the first Mars colonists will not be pioneers. They will be casualties in humanity's most ambitious experiment. The perchlorates in Martian soil remain toxic. The radiation bombardment continues unabated. The psychological toll of isolation in a world that offers no sound, no wind you can feel, no horizon that holds life. These challenges are not solved by engineering alone. And yet, despite knowing all of this, despite understanding the horrifying vulnerability of human flesh in such an environment, we will still go. Why? Because the same forces that drove our ancestors to cross frozen tundras and vast oceans still pulse within us. Because Mars represents not just survival, but transformation. Because somewhere in our collective consciousness, we understand that becoming a multi-planetary species is not optional if we wish to endure across cosmic time. The dangers are real, the deaths will be real. But so too is the potential for humanity to transcend the boundaries of a single fragile world. Your personal Mars survival timeline depends entirely on the infrastructure around you. Naked, you have seconds. Suited, you have hours. Sheltered, you have months. Supported, you have years. Established, you have generations. This is not speculation. This is physics, biology, and engineering converging to define the boundaries of what is possible. The terrifying truth is that Mars offers no mercy, no second chances, no forgiveness for miscalculation. But perhaps that is precisely what makes the endeavour so profoundly human. To look at a world that wants to kill us in every conceivable way, and still choose to plant our flag in its frozen soil. If this journey through Mars survival has changed how you see the red planet, if it has given you a deeper appreciation for the sheer audacity required to reach another world, consider leaving a like on this video. Your support helps this channel continue exploring the profound questions of space, survival, and humanity's place in the cosmos. Subscribe if you want to join future journeys into the unknown, where we examine not just where we might go, but whether we can truly survive when we arrive. And here is something I am genuinely curious about. Where are you watching this from? Are you on Earth? Perhaps dreaming of distant worlds? Comment below with your location. Let's see how far across this planet our community reaches. If you found exceptional value in this content and want to support the channel further, YouTube memberships are available, though completely optional. Either way, thank you for taking this sobering journey with me into the realities of Mars survival. The clock is always ticking. The question is, how much time do we really have?